13, Ohm's law, resistance and resistors, clarifications. So here's what I was mentioning, resistivity. So the resistance of a wire or component in a circuit is directly proportional to its length. It's also inversely proportional to cross-sectional area, and it's directly proportional to the resistivity of the material. So resistivity depends again on the available valence electrons. Something like aluminum has a relatively large resistivity. Something like gold has a relatively small resistivity. So for any particular length and cross-sectional area, the material influences the resistance. Longer wires have larger resistance, and larger cross-section wires have smaller resistance. We will not be responsible for knowing this equation in the AP exam, but we will be talking about the idea of it. You can consider a pipe and the amount of water that flows through the pipe, especially in terms of cross-sectional area. A larger diameter pipe allows more water to flow, and similarly, a larger diameter wire allows more current to flow, or allows current to flow more easily. Resistance also changes with temperature, so resistivity gets larger as temperature increases. We are not concerned with the relationship between resistivity and temperature for the most part. It's simply a side note. And then semiconductors are complex materials that have resistivities that tend to decrease with temperature. And again, semiconductors outside of the scope of this course, but something of interest for later. So finally, in this section, we want to discuss power, electric power. So we're getting used to this idea that voltage has to do with electric potential energy per charge, and it also has to do with a sort of push of charges through a circuit. So power still means the rate of change of energy transformation. However, energy, at least electric potential energy, is equal to the amount of charge times the electric potential, because electric potential is defined as electric potential energy per charge. So we can rewrite power as QV, amount of charge times amount of voltage available, divided by time, and then charge per time is defined as current. So we can either consider power in a circuit or power in an electrical element to be charge times voltage divided by time, which is equivalent to electric potential energy per time. Or we can write it as power is equal to current times voltage. They're interchangeable. If you've done circuit stuff, you're probably more familiar with power is equal to current times voltage, P equals IV. So just as before, the unit of power is the watt, joule per second. And for ohmic devices, we can replace that V for voltage with IR, V equals IR for ohmic devices. So for an ohmic device, we can also write power as I squared times R, or V squared divided by R. P equals IV is always true. P equals I squared R, or P equals V squared over R is only true for ohmic devices. I'm actually just going to skip this, but 1 kilowatt hour. So 1 kilowatt, so watt is a joule per second, is 1,000 watts times 1 hour, 3,600 seconds. So a kilowatt hour is a measurement of energy, like sort of energy distributed or energy transformed. And it's approximately 3.6 times 10 to the 6th joules. So let's do some example power problems. I'm going to look at problem 30A, problem 31, and problem 32, but I'm going to do so with the document camera so we can solve the problems together.